Hello, guys. Today I would like to talk about discrete time Fourier transform. Previously we talked about uh, like Fourier series for periodic continuous time signals. Again, we said Fourier series for periodic discrete time signals. And last week we mentioned Fourier transform for aperiodic continuous time signals. And today I will mainly focus on Fourier transform for aperiodic discrete time signals. That's why it's called discrete time Fourier transform. Okay, so we will abbreviate it as DTFT. So if we talk about discrete time Fourier transform, we will mainly discuss this formulation, and then you will see this x of n is my aperiodic discrete time signal, and then my formulation will be 1 over 2 pi for one period, and x e to the j omega times e to the j omega n d omega. You see here, this time I said x e to the j omega. If I say x j omega, it means continuous time Fourier transform spectrum for this continuous time Fourier transform. If I say x e to the j omega, it means discrete time Fourier transform. Okay, what is this equation doing? It's a synthesis equation. What does synthesis equation mean? I will synthesize my signal x of n by combining all the cosines and sines by multiplying them with our coefficient x e to the j omega. These are my discrete time Fourier transform coefficients. Okay, these are discrete time Fourier transform coefficients. If I look from the other perspective, x e to the j omega, if I know x of n, and if I would like to find out the coefficients, then I will say x from minus infinity to plus infinity, because my signal is aperiodic and it can go from minus infinity to plus infinity, and then I will say x e to the j omega n. You see, there is no omega 0 here, guys. Omega 0 means repetition. Omega 0 means periodicity. There is no periodicity in aperiodic signals. That's why we use this formulation, okay, this formula, and then this formula, okay? And then this formula means I am doing an analysis, okay? And it's an analysis equation. Analysis means we are decomposing our signal x of n into sines and cosines, and we are trying to find out the similarities between x of n and sine and cosine. We said that it's like a kind of correlation coefficient, and we are trying to find out the similarity between my signal x of n and e to the power j omega n, which is like sine omega n, cosine omega n in real axis and in imaginary axis. Okay, so this is a critical thing, and then we should be aware of the situation that if we talk about this, okay, like this means my Fourier coefficients are periodic. My signal x of n is not periodic, but my x e to the j omega is a periodic, okay, is a periodic function, okay? So this is a function which is like discrete signal, and this is not a discrete function, it is rather a continuous function. Okay. So let's move on. Periodic in 2 pi. Okay, this was something that we discussed when we were talking about continuous time, discrete time Fourier series also. Let me talk about one question. I will solve 3 questions at this point and then finish the video at this point. Let's say my x of n is equal to Dirac n, and I'm trying to find out the coefficients for this function. And then I'm going to write x of n e to the power minus j omega n, and going from minus infinity to plus infinity. And then I'm going to write Dirac n e to the power j omega n, and goes from minus infinity to plus infinity. If you think about this, Dirac n is equal to 1 when n is equal to 0. That means x e to the j omega is going to be equal to, only for n equals 1, for n equals 0, this will be 1, okay? This is 0, this is 0, e to the power 0 is 1. So then I'm going to write 1 as my spectrum, and then I will draw my spectrum like this, okay? From minus pi to pi, it's always 1, okay? X e to the j omega. And then this is there is no imaginary part, it's only real part, and then it's a real coefficient, and then there is no phase term here. If we talk about x Dirac n minus n0 as my x of n, then I'm going to write again from minus infinity to plus infinity Dirac n minus n0 e to the power minus j omega n. Then this means n equals n0, Dirac n minus n0 is equal to 1. So this will be n0, okay? And all the n's will go away and only n0 will be in place. So I'm going to write as my coefficient x e to the j omega be equal to 1 times e to the power j omega n0, okay? So that means my magnitude is still 1, okay? The magnitude of my function or my Fourier transform coefficients or the spectrum will be 1 all the time, but this is again magnitude. If we will talk about the phase, then the phase will be equal to minus omega n0, okay? This is the phase term, and then it's between minus pi and pi. As I said, between like 0 to 2 pi or from minus pi to pi, it's the same thing that we should be aware of, okay? So I hope you understand this is the phase shift term. This is the absolute value magnitude term. This magnitude is called magnitude response if it's a filter, okay? Magnitude response. And this part will be my phase response. And then magnitude response will give me the information how much the magnitude of this signal is effective. And when we multiply two things, this only in terms of magnitude, this one will be effective. And in terms of the phase response, how much this function will have an effect on the phase of the other signal. Okay, so if there is a time shift in my signal, it means there is a phase shift in frequency domain. Okay, so it was 1 when Dirac n was my function. Now it is 1 times e to the power minus j omega n0 when my signal is Dirac n minus n0. Okay, so let's move on and try to give you one more interesting function, which is x of n, and you will see this a lot in in your books or in many places, if a is less than 1 and my x of n is going to be a to the power n and un. If we want to plot this, it will be something like that, right? So n is, a is less than 1, and this is a is sorry 1 a squared a cubed and then a to the power 4 and so on. So this is my a, this is my function, and I would like to find out x e to the power j omega using the formula as such, and then n is equal to minus infinity to plus infinity, and then I'm going to write my x e to the j omega, and my n is going to be from 0 to infinity because this is un, and then I'm going to write a to the power n e to the power j omega n. Okay, this a will come here, and then this e to the power minus j omega will come here, and this un will be shown in my boundaries. Okay, boundaries of my summation. So how should I proceed? I should proceed as such. Then I'm going to write n is equal to from 0 to infinity a e to the power j omega and common n. N's are common here, so I can put like that. And then if you remember from the infinite sum formulation, it's like 1 over 1 minus a e to the power minus j omega. Okay. So if you remember from circuit theory or differential equations, up to now, we always dealt with continuous time signals, continuous time systems. Now, for the first time, we are starting to talk about discrete time, and there will be discrete time systems and discrete time signals, and we will be talking about the Fourier transform of discrete time signals. Okay. So this is my x e to the j omega, 1 over 1 minus a e to the power minus j omega. If you would like to find out the magnitude response, then it will be 1 over 1 minus a e to the power minus j omega. And then I will take the magnitude of this. And you know this e is like cosine omega minus j sine omega. That's why I will write 1 over 1 minus a cosine omega, and then minus j a sine omega, and then this will be like that. This part will be the real part. This part will be the imaginary part. So if we think about this, then it will be like 1 over 1 minus a cosine omega, and then take the square plus a sine omega square, and then take the square root. Okay, this is the magnitude response of my e to the a to the power n un. Okay, this is how I do it. And then finally, if you do these things, you can do them at home, and then x e to the power j omega will be equal to 1 minus 1 2a cosine omega plus a square. Okay, so I want you to draw this in MATLAB and see what kind of a function is this. Okay, so is this a low pass filter? Is this a high pass filter? For what kind of a it will be, the graph of this function will be like. If the graph is something like that, then it will be low pass filter. If the graph is something like that, the filter will be high pass filter. Okay. So one final question, and then I will finish this video. If we have this filter h of n, which is like 0, 1, and 0, if it is less than minus n1, it is 0. If it is greater than minus n1, and less than n1, it is 1. And if it is greater than n1, it is 0. So if I take a look at this, the graph of this function, it will be something like that, okay? 0, 1, and this is n1, 0, 1, minus 1, and minus n1, okay? So n1 maybe 2, 3, 4, it may be different, okay? For n1 equals 2, this will be 2 and minus 2, okay? So let's do it in a general format. X e to the j omega will be equal to, I will write my my formulation again, from minus n1 to n1, 1 times e to the power minus jn1, j omega n, okay? This is my signal, and I put the boundaries of my signal here. The value at 1 will be over here, and then I'm going to write e to the power minus j omega n. So what is next? Then I should write this here, and n is equal to minus n1 to n1, and then e to the power minus j omega to the power n, and then it's going to be like sine omega n1 plus 1 over 2 divided by sine omega over 2, okay? I want you to go over this and find out how I found this one, okay? So please go with, take a look at this formulation and then do some exercises on your own, and then see if you understand, if you have any problems with understanding this, this topic, okay? See you in the next video.